For most of human history, the universe appeared simple and unchanging. The stars seemed fixed in place, the galaxies beyond our own were unknown, and the cosmos itself was often imagined as eternal. Modern astronomy has completely transformed that picture. With every new telescope, every spacecraft, and every generation of observations, our understanding of the universe has evolved. Ideas once considered certain have been refined, expanded, and sometimes replaced as new evidence emerged. One of the greatest scientific revolutions came during the early 20th century. Astronomers discovered that the Milky Way was only one galaxy among countless others scattered across the cosmos. Soon afterward, observations revealed that these galaxies were moving away from one another, showing that the universe itself is expanding. This remarkable discovery changed everything. Instead of an unchanging cosmos, scientists began describing a universe that had evolved over time from an extremely hot and dense beginning. Today, decades of observations, including measurements of the cosmic microwave background, stellar evolution, and the expansion of space, indicate that the universe is approximately 13.8 billion years old. That number is not simply another statistic. It represents generations of scientific progress and reminds us that every conclusion in science remains open to improvement as better observations become available. Even our own galaxy continues to present unanswered questions. The Milky Way contains hundreds of billions of stars, vast clouds of gas, and countless planetary systems. Yet when astronomers measure how stars move around the galactic center, their motions cannot be explained by visible matter alone. Something unseen appears to provide additional gravitational influence. The leading explanation is dark matter, an invisible form of matter that neither emits nor reflects light but interacts through gravity. Although scientists cannot observe dark matter directly, its effects appear throughout the universe. Recent measurements from the Gaia Space Observatory have mapped the positions and motions of nearly 2 billion stars with extraordinary precision, providing one of the most detailed views of our galaxy ever assembled. These observations continue to improve estimates of the Milky Way's structure and total mass, while also helping researchers test models of how dark matter may be distributed throughout the galaxy. Each new dataset adds another piece to a puzzle that remains incomplete. Looking beyond the Milky Way reveals an even more surprising picture. Modern observatories such as the James Webb Space Telescope have detected galaxies whose light has traveled for more than 13 billion years before reaching Earth. These observations allow astronomers to study the universe during its earliest stages, when the first generations of galaxies were beginning to emerge. Many of these distant systems appear larger, brighter, and more chemically evolved than earlier models predicted. Rather than finding only small collections of primitive stars, astronomers have observed galaxies already forming stars at remarkable rates. These discoveries do not overturn the Big Bang model, but they encourage scientists to refine theories describing how rapidly galaxies assembled during the universe's first few 100 million years. The story of cosmic evolution may be more dynamic than researchers once imagined. At the same time, another field of astronomy has experienced extraordinary growth. Just a few decades ago, no planets had been confirmed around Sun-like stars beyond our solar system. Today, thousands of exoplanets have been discovered. These distant worlds display astonishing diversity. Some orbit extremely close to their stars, completing an orbit in only a few days. Others travel along highly elongated paths or exist within multiple star systems. A number of rocky planets orbit within regions where liquid water could exist under suitable conditions, making them especially interesting targets for future study. Powerful telescopes have also begun examining the atmospheres of some exoplanets. By studying how starlight passes through those atmospheres, astronomers have detected molecules such as water vapor, carbon dioxide, methane, and other gases. One well-known example is WASP-96b, where observations revealed water vapor together with evidence of clouds and atmospheric haze. Although this hot gas giant is not considered habitable, its atmosphere demonstrates that complex chemistry is common throughout the galaxy. Every new observation improves our understanding of how planetary atmospheres form and evolve. More importantly, it suggests that the ingredients necessary for life may be widespread across the cosmos. As astronomers continue exploring the cosmos, one conclusion has become impossible to ignore. Everything we can directly observe, every star, every planet, every glowing nebula, and every galaxy, represents only a small fraction of the universe. Current observations indicate that ordinary matter makes up less than 5% of the total cosmic energy budget. The remainder appears to consist of two mysterious components: dark matter and dark energy. Although neither has been observed directly, both reveal themselves through their influence on the universe. Dark matter acts as an invisible source of gravity, helping galaxies and galaxy clusters remain bound together. Dark energy, on the other hand, is associated with the accelerating expansion of space itself, causing distant galaxies to move away from one another at an ever-increasing rate. Understanding these hidden components has become one of the greatest challenges in modern physics. Future observatories, including the Nancy Grace Roman Space Telescope and next-generation ground-based surveys, are expected to provide new clues by mapping billions of galaxies and measuring how cosmic structures have evolved over time. Among the many fascinating objects studied by astronomers is a nearby ancient star known as HD 140283, often nicknamed the Methuselah star. Early measurements suggested that the star might be older than the universe itself, creating an apparent paradox. As observations improved, scientists refined both the star's estimated age and the uncertainty surrounding those measurements. Today, the best estimates place its age close to that of the universe, with overlapping uncertainties that remove the contradiction. Rather than challenging cosmology, the star demonstrates how scientific measurements become more accurate as better instruments and improved analysis become available. Astronomers often use a simple analogy to illustrate the immense age of the cosmos. Imagine compressing the entire 13.8 billion-year history of the universe into a single calendar year. The Big Bang occurs at the first moment of January 1st. The Milky Way gradually takes shape months later. Our solar system does not appear until the final days of December. Earth forms only near the very end of the calendar. All of recorded human history occupies just the final seconds before midnight on December 31st. This perspective reminds us how brief humanity's existence has been compared with the age of the cosmos. Every observation we make represents only a tiny glimpse into an unimaginably long story. The age of the universe itself is determined through several independent lines of evidence. Astronomers measure the expansion of space by observing the redshift of distant galaxies. They study the faint glow of the cosmic microwave background, the oldest light we can detect. They compare these observations with models of stellar evolution and the distribution of galaxies across the universe. Together, these independent methods consistently support the current estimate of approximately 13.8 billion years. Science, however, is never about protecting ideas from revision. Whenever new evidence appears, researchers test it carefully, compare it with existing models, and refine their understanding where necessary. That willingness to question established conclusions is one of science's greatest strengths. Recent observations of extremely distant galaxies provide a good example. Some galaxies observed during the universe's earliest epochs appear surprisingly bright and well-developed. Rather than overturning our understanding of cosmology, these discoveries encourage astronomers to improve models describing how rapidly the first stars and galaxies formed after the Big Bang. Every unexpected observation becomes another opportunity to learn. The universe has repeatedly demonstrated that it is more diverse and more dynamic than previous generations imagined. Galaxies collide and merge. Stars are born inside enormous clouds of gas before ending their lives in spectacular explosions. Black holes shape the centers of galaxies. Planetary systems evolve over billions of years, while new worlds continue forming around distant stars. Every level of the cosmos reveals another layer of complexity. Perhaps the most remarkable lesson is not that we have solved the universe. It is that every answer leads to even deeper questions. Each discovery expands the boundaries of human knowledge while revealing how much still remains unexplored. New telescopes do not simply confirm what we already know. They uncover phenomena we never expected to find, opening entirely new fields of research. The universe continues to surprise us because it is far richer than any single theory or observation can fully describe. As technology advances, future generations will observe farther into space, measure cosmic structures with greater precision, and investigate mysteries that today remain beyond our reach. The pursuit of astronomy has never been about reaching a final destination. It is a continuous journey of exploration, driven by curiosity and guided by evidence. And with every new observation, the cosmos reminds us of one timeless truth. The more we discover about the universe, the more extraordinary and mysterious it becomes.